First, I think, thanks to the students for organizing the coffee. When I came in this morning, I was half expecting that these coffee shops would be open, and I was wondering what I was going to do if I had to talk without having my morning coffee first. So thanks very much, guys. I appreciate that. Over the course of this session, I've sort of been following the discussions and the interests, and as a consequence have been taking this talk and kind of changing its focus. My original plan, or where I was originally planning on going with this, is very far from where what I'm actually going to talk about today. But there hasn't been much discussion of magnetic field in the workshop so far, but I do think that it actually has a pretty important role in many of the topics and many of the issues that you guys are thinking about, in particular connected with sort of the early Earth and its early thermal evolution and sort of what would be the nature of this style of convection in the mantle in an early Earth and what constraints the magnetic field plays on that. When people that do this stuff generally have a variety of different motivations for doing it, for the pure point of thinking about the dynamics of the core and thinking about the way in which the magnetic field gets generated, the issue is largely one of thinking about how is it that you can organize flow, a convective flow in the core, and organize the structure of the magnetic field such that that flow continuously regenerates the magnetic field. We know that for typical properties of the liquid iron core, its electrical properties and other sorts of things, that if the field wasn't actively generated, it would disappear on timescales of sort of tens of thousands of years. And so it has to be always actively maintained, and the fact that it's actively maintained tells us something about the dynamics of the system. A lot of effort going into thinking about how these flows get set up, how this process actually works in detail, and I'll talk a little bit about the numerical models, which have been really, I think, striking in terms of their success, but I'm going to show you at the end and really kind of focus at the end on how much further those models have to go before I think we can reliably apply them to the Earth. But even if we don't understand in detail how the flow actually generates the magnetic field, there's sort of a thumbs up, thumbs down issue. Field or no field can tell us a lot about the intrinsic internal state of the planets. And the point is that planetary dynamos are very, very sensitive diagnostics of the internal dynamics of planets. And so there's no expectation that a terrestrial planet will have a dynamo. And we just simply have to look at our own inner solar system to know that this is the case. So we have a field actively maintained on Earth today, not on Mars, not on Venus, and surprisingly, to me at least anyways, that there's an actively generated field on Mercury. And so we'll try to understand, and in fact most of the effort will go in this talk, to try to understanding why it is that terrestrial dynamos are sort of such a uncertain issue with respect to generating fields. The other point, I guess, is, and the great thing about these, if you're thinking longer term in terms of exoplanets and terrestrial exoplanets, is at least this is a diagnostic, an internal diagnostic, that in principle you might be able to see from space. And lastly, in the sort of the spirit of the theme, did the early Earth have a magnetic field? And we'll see whether there's an answer to this question or not. A couple of observations that bear on this. These may be the only observations that I show. And one of the good things about at least this issue of the internal state, all I need to know really is whether there's a field or not a field. The details, in some sense, are sort of a secondary issue. So that makes it a lot easier to deal with. But the observations that we have on this question are essentially two. We do know that we have paleomagnetic evidence for a field at about 3.45 billion years. There had been a number of samples. It's sort of an interesting area of research, discussions and debate about whether some of the earlier samples were reliable. I think most people would accept this value and then infer that the internal state of the planet must be such that it's able to generate a field at 3.5. And I think that's a really important constraint that any thermal model history is going to have to reproduce. And there are these more tenuous observations of the possibility that the Earth did not have a magnetic field early in its history, and this is a paper that came out I think in Nature in 2005. And what they're doing is they're measuring the nitrogen isotopic ratio in lunar soils, and they're noting that it looks like there's two reservoirs, essentially, of nitrogen isotopes. One which you would characterize as being the isotopic composition of the sun, which is implanted presumably in the surface of the moon by the solar wind. And then another source, which had been attributed to an atmospheric contribution from the Earth. And so the idea here is that if the Earth didn't have its magnetic field protecting the atmosphere from the solar wind, if that field collapsed, then perhaps the solar wind could sputter some of the atmosphere off, and if the moon was sort of lined in the right location, it could receive some of that nitrogen and give rise to this isotopic source. And so they would infer that maybe there was no field at 3.9 billion years. The way you would test this is look to see if there's no evidence, at least no evidence of these nitrogen isotopes on the opposite side. And so at least for the foreseeable future, that's not going to be a testable hypothesis. So that's a safe one for a while, but it's sort of an interesting idea. The point, I guess, here is that just simply on or off has implications for the Earth, and it probably tells us a lot about the style of convection in the mantle, not the core. Okay, so here's the strategy. I'm going to sort of provide a little bit of physical setting and processes. Jackie talked a little bit about some of the things, and so all those slides came out, which is good. So we'll finish well on time, I think. And then I'm going to try to stitch together these processes to just show you how they work in terms of constructing thermal evolutions. And we use those ideas to make estimates for the amount of power that's available for driving the magnetic field. And we'll see how that works. And I'm going to spend most of my time actually dealing with these two things because they really do tell us something about the early Earth, perhaps, and its early thermal evolution. But then at the end, I can't help but come back to this point of the convection in the core, the magnetic field generation, where we are with numerical models, and maybe where we're likely to go and possible lines of future advance. Okay. So here's a picture of the physical processes that we think are relevant for the core. The core is largely driven by the fact that the mantle extracts heat from the core, and the core then, in effect, responds to that heat transport. So the mantle is drawing heat out of the core. This causes the core fluid to cool, probably thermally contract a little bit. That just can produce cold, downwelling fluid at the top boundary. But also, as you're cooling the core, you're going to sort of begin to crystallize the solid inner core. And as Jackie was pointing out, it freezes from the inside out just because of the pressure dependence of the melting temperature. It reaches, for a given adiabat, it will cross the melting curve first at the center and then gradually migrate out. And so the solidification process will give rise to latent heat, which is a source of buoyancy. But we also know that there are light elements, impurities that are dissolved in the core. And we believe, based on the densities of these different regions, that some of those impurities are excluded from the solid and therefore provide a source of buoyancy for driving convection. And so the combination of perhaps thermal downwellings from the top, chemical buoyancy, and thermal buoyancy connected with inner core growth are all driving convection and all have to be, or are at work probably in the present-day Earth. So if we want to constrain this process, we'll need to know something about the thermal state, what's the amount of heat that's coming out of the core today, and we can make guesses, rough guesses, based on sort of our current thinking about the temperature structure inside the planet. We know that the potential, the adiabatic temperature, sort of the potential temperature at the surface, is about 1600 degrees near the top of the mantle, based on the amount of melting that takes place and the thickness of the oceanic crust. We've got phase transitions and other sorts of markers that tell us something about temperature in the upper part of the mantle. And we can extrapolate that adiabat all the way down to the core mantle boundary and get some number which is sort of roughly in that range. And as Jackie also pointed out, that the boundary between the inner core, it's whatever iron alloy it happens to be, and the fluid defines essentially the melting temperature at that particular pressure. And there's a lot of uncertainty still about what that temperature is. The debates, I remember from the time when I was a graduate student, Raymond Johnlow and Reine Bowler battling it out at AGU meetings and lots of betting going on, name calling, that sort of thing. The temperatures have gone up a little bit, but they're still uncertain by quite a wide amount. And so, but if you take this range of temperatures, sort of anchored at the inner core boundary, and extrapolate them up, you get sort of a range of temperatures at the base of the mantle, perhaps in this range, and they're different. And they're different by something on the amount of sort of 1,000 to maybe as much as 2,000 degrees. And so, based on the first lecture, at least that I gave, on mantle convection, you know that you expect these thermal boundary layers at the top, where you basically allow heat to be conducted into this layer before it gets transferred by convection. And so the existence of this boundary layer at the bottom should come as no surprise. So here we'll just zoom in on that and the way we would construct an estimate for the heat flow based on the thickness of that boundary layer, and what that thickness actually is of course also a question. But here's our well-mixed region up here. We've got this thermal boundary layer where we're bringing heat into the mantle. If we knew what this temperature jump was, and we knew what the thermal conductivity of the lower mantle minerals were, and we also knew the thickness of this boundary layer, we could make an estimate of what the heat flow is across the core mantle boundary. And of course, we don't know all these things very well, but it never stops us from making estimates, right? And so, typical estimates might be 5 to 10 terawatts. There has been a tendency to sort of move these values up with time. And so here's another thing, Ed, you might want to make a plot of CMB temperatures as a function of time. There's definitely a trend there. They're definitely going up. But that's a plausible number, and we'll come back and maybe revisit this later. But the question you could ask is, well, is there a corresponding thermal boundary layer on the other side, on the core side, right, where we have to get heat from the core, which is being carried by convection, and get it through into the mantle? Is there such a thing? And the answer is maybe, but not necessarily. And the issue is this. If you have a core that is producing a dynamo, it's convecting, it's well mixed, basically, then you would expect an adiabatic temperature profile inside the core. And as a consequence, you have some prediction of what the temperature gradient would be through the outer core in a well-mixed state, the sort of so-called adiabatic. And because metal is a good thermal conductor, and this is the reason why we make frying pans out of metal as opposed to granite, right, is that they're good thermal conductors, it turns out that adiabatic gradient for a plausible value for the thermal conductivity can carry a substantial amount of heat by conduction toward the boundary. Okay? And so these numbers that are carried by conduction are not so different from these numbers here that the mantle's taking out. And so the way you want to think about this is, if the mantle takes out a certain amount of heat and the core can supply all that heat by conduction, what's the point of convecting? It's not motivated to do so. And so the issue is that because these numbers are so close, the operation of convection, thermal convection at least in terrestrial planets, is really kind of on a knife edge. It's not clear. Inevitably that it will have a dynamo, and this is partly what makes it so useful for gaining insights about the thermal state of planets. Okay, so those have been the numbers that I would have used maybe a year ago. There was a paper that came out probably a couple of months ago that reported that the thermal conductivities of iron might be a factor of 3 higher. So these, if you just accept those values as being correct, you're coming up to these sorts of values for the heat conducted out of the core. And so now these are right in the range of these guys. And so now it's anybody's guess as to what's going to happen. We can identify at least a couple of end-member cases and sort of see what might be the possible outcomes of this. This would be the case that we might have imagined a decade ago, perhaps, where the heat flow that the mantle's taking out, so the mantle decides on this, it's in charge, basically. If this value is greater than the amount of heat that you can conduct down the adiabat, okay, then you would expect these cold thermal downwellings. You sort of can see it here, right? I've got conduction bringing heat into this boundary region. The mantle is taking more away, and so this region inevitably is going to cool down. And so I will have, in this case, a thermal boundary layer at the top. I'll producing cold fluid. That cold fluid will go unstable. It will sink down. It's exactly the style of thing that we talked about in the mantle convection lecture. So that's great. And so we get this buoyancy, we get these sorts of sources of buoyancy, we can drive pretty vigorous convection in that way. But it's clear, it's also possible that the heat flow that the mantle takes is actually less than you can conduct toward the boundary. And so we don't get a thermal boundary layer in this particular case. If you imagine here's the mantle heat flow, it's taking out less than you can supply. And so this region's all well mixed by convection. It's generating the dynamo. We're conducting more heat to this region than we take away, so this region's going to warm up. We're going to get a sort of a warm, stratified layer on the top. And there's a couple of options, a couple of things that could happen. We might, if the inner core is growing and we're getting compositional buoyancy, it's not impossible that this compositional buoyancy can sort of entrain some of this fluid, mix the warm fluid down. Of course, to do that, the convection has to do work on the system to take hot stuff and move it down. It requires work to be done, and that's diverting energy that would otherwise be available for powering the field. My own guess is that this probably is not going to work. It's more likely that you're going to get a thermally stratified layer at the top. But it's actually kind of interesting, because once you make a thermally stratified region at the top, of course, you continue to get inner core growth, so the light elements are going to accumulate in this region here. And so this region underneath is going to become compositionally lighter than the overlying region. You can get double diffusive sort of fingering type convections. But there are going to be compositional variations, radial compositional variations, that would be compatible with the seismic observations of fast regions here, although I don't honestly expect the variations in composition to be big enough to explain those results. So it's interesting. So the point is that the core could be convecting in a variety of different ways. If we go back to the early Earth, though, a time when there was no inner core, presumably, and the only game in town is the production of cold fluid at the top, then if you have the situation where the heat flow that the mantle is taking is less than the adiabatic value, then convection is going to cease. And when convection ceases, you don't get a dynamo. So there is more fine print. I always like to do this. You sort of have to read the fine print. It's possible that we could get out of this, and I'll show you maybe just how this might work, but there may be possibilities for having chemical interactions sort of get us out of this. On the other hand, if the heat flow that the mantle takes out of the core is greater than the adiabat, then sure, we'll get thermal convection, and that thermal convection will presumably generate a magnetic field. So we don't need an inner core to make things happen. It helps, obviously, but you do need to have buoyancy being produced to drive the flow. Okay, just briefly on the core-mantle interactions, the idea here is that as you cool the core, some of those impurities which dissolved into it become supersaturated, exceed their solubility, and begin to precipitate out. And so if you imagine, for example, that this was silicon for some reason, that it was oversaturated, as you cool a mixture of iron and silicon, and you start to take silicon out of the liquid, then what you've got is a compositionally dense fluid relative to the underlying region, and so you get this sort of downwelling. So essentially compositional buoyancy driven by downwellings. You know, and you could do this in a variety of ways, I suppose. When Dave Ruby was talking about the issue of putting silicon into the core early days and then subsequently adding oxygen at later times, it's not implausible that the later addition of oxygen, as the mantle becomes oxidized, could actually drive silicon out of solution. They're not precluded from both being there, but I think you would expect as oxygen increases, the solubility of the silicon potentially could go down. Let me just make this point, and again, this is something that Dave touched on. Experiments do tend to suggest that these major elements are undersaturated at present, with possible caveat that there's some interaction between these two, but there could be other elements, and Dave, for example, has suggested that magnesium might play an important role in this story as well. Okay, so let's start to put some of this stuff together in terms of thermal history models. If we want to think about how fast is the inner core growing, we can really do that based on energy conservation, just the first law of thermodynamics. And so what I've done here is drawn the sort of in the symbolic form that you see it in a thermodynamics textbook, and I've just partitioned the internal energy and just sort of separated out a separate gravitational part here. There's the internal energy, the gravitational energy, the heat that we're taking out of the system, and then the work done by pressure. And what you typically do in these sorts of things is you assume that the core evolves through a sequence of states which are hydrostatic and adiabatic and well mixed. It's certainly true that the fluctuations, at least in the core, relative to that well-mixed adiabatic state is pretty good. I mean, these temperature anomalies here, the magnitude of those temperature anomalies that are required to drive the flows that we infer from variations in the magnetic field are on the order of millikelvins. And so the picture that you should have is one of a sort of a nominally adiabatic fluid with millikelvin variations about it, and we're just simply going to average over those and not worry about the convective fluctuations. Okay, so if you do that, what you find is that all of the gravitational energy that gets released by the thermal contraction essentially is completely balanced by the work that the pressure forces do as the core collapses. And so we can just subtract that piece off, and then what we end up with is something that looks like a heat budget. We're taking out a certain amount of heat, then we're getting a certain change in the gravitational energy, and the star just simply refers to the fact that it's only the part due to compositional rearrangement. And then we have the internal energy, which include things like secular cooling, latent heat. I suppose in principle I could include radioactive heat sources in this. Why not? Internal energy is just the bucket of everything that we don't want to specifically keep track of, right, more or less. So we could put that there, and then there's the separate gravitational energy here. Okay. So prescribe a heat flux, then all of these other things are defined with our well-mixed adiabatic hydrostatic state. We can predict things like how fast the inner core grows. And so here's a model, a simple model with a, yep? Question, yeah, sure.
Latent heat creates hot fluid at the inner core boundary.
Yes.
As a source of buoyancy.
Yes.
But radioactive heat is that generating a source of buoyancy in the core that drives motions to help the field grow, or is it just kind of damping it?
So the question is, does radioactivity actually help to drive the flow? And the answer is, as long as you've got cold downwellings coming from the top, the answer is yes. If you don't have cold downwellings coming from the top, then the answer is no. And in fact, what I'm going to show you in just a minute is show you essentially Carnot efficiencies. And what you'll find is that the Carnot efficiency for sort of the secular cooling or the radioactive contribution is very different from the secular cooling for latent heat. And part of the reason for that is you can kind of imagine it this way. In this case, I'm taking heat from the bottom and moving it all the way to the top, some sort of thermal buoyancy, taking it from here and moving it all the way to here. Whereas when I'm cooling the core, I'm kind of taking buoyancy from the volume and moving it to the boundary, in essence. And it's much less efficient. The secular cooling is much less efficient, for example, than latent heat for that reason. Does that sort of answer?
So
maybe not quite. So radioactive heat is exactly equivalent to secular cooling. Yeah, exactly. Okay, so here is this sort of simple model to just sort of put numbers into your minds. This is for the case, just very idealized, 6 terawatts of heat coming across the core mantle boundary for all time, right? Implausible, but it gives you a sense of scale, I think. So here's a plot of the inner core radius as a function of time, so 0 here going back. You know, it's interesting. I guess maybe this is true in this community, but if you look at the paleoclimate community, there's 2 different groups, right? And they run time in opposite directions, and you always have to flip diagrams back. I suspect this is different from some of the stuff that Rick showed, for example. Apologies, right? But so here's present, right? Here we are at the present. There's the inner core radius at just over 1,000 kilometers. But the point is that for that heat flow, we're talking about an inner core nucleating and growing at about 1.5 billion years. And then no inner core back here. And so if the only chemical buoyancy in town is associated with inner core growth, then for this period of time, including the 3.4 billion years, we have to have thermal convection doing the job for us. Okay. Here's just an estimate of the temperature at the base of the mantle, the top of the core. This initial value, I don't remember exactly, maybe 3850 perhaps, in the range of the values that we expect. Going back in time, the inner core forms, and then we cool slightly faster. So latent heat and the gravitational energy release, you could kind of think of those as being contributions to the specific heat of the core. And then once those things are gone, that same heat flow will actually allow us to cool back in time a little bit faster. Okay. So the thing is that the thermal evolution models based on conservation of energy tell us nothing about the power that's available to run the dynamo. Right? The dynamo is irrelevant. It's this process that converts energy from one form to another, but it doesn't really alter the overall energy balance. And so thinking about inner core growth or these global energy balance or global, how can I say it, sort of thermal evolution or heat budgets, they don't tell us anything about the dynamo. To do that, there's a variety of ways that we can do this. And one of the ways that's maybe most insightful, perhaps, is to think about the entropy balance in the core. And this is just a little cartoon to illustrate the sort of the simple idea of a Carnot efficiency. And then we'll see how to extend that over to the case, a slightly more complicated case of the core. So here's the picture that I've drawn before. Again, putting in hot at the bottom, we're putting in heat through the thermal boundary layer, we're getting convection, we're taking heat out the top. And for a steady state system, we're going to put as much heat in the bottom as we're going to take out the top, right? So that's the picture that we talked about in the mantle convection state. But if you think about the entropy that you're putting in, well, that's just the rate of entropy going in. It's just the heat flux divided by the temperature at which we're putting that heat in, right? So that's the amount of entropy, the rate of entropy flux that we're putting in across this boundary, and it's different from the amount that we're taking out the top simply because the temperature at the top is a little bit lower, right? So we're putting in a certain amount of entropy in the bottom, but it's not so much because the temperature is high. And then we're taking a little bit more entropy out the top than we're putting in the bottom. So somewhere in the interior, we must be producing entropy that will balance this difference. And the idea is that the fluid convection does work, and it dissipates. It does mechanical work, either in this convection or producing a dynamo. And that dissipation essentially will contribute to the entropy production. And we think in the core that most of the work that the convection actually does is in powering the dynamo. So that may or may not be true, but that's a common assumption. And so we think of this dissipation as being the dynamo power. You know, the dynamo is doing this work, it's dissipating, it's essentially it's exhaust for the dynamo. So if you think about when we were walking back and forth to the lunch, right? And when they were having those the music blaring out really high, if you were to put your hand on the amplifier, it would be really warm, right? And that's this. It's the electric currents going through a finite electrical conductivity material produces lots of heat. And we think that this is what the dynamo is doing. And so we measure the dynamo power by the dissipation that it produces. And so I'll use those interchangeably, but they have to be related, right? And so here's the idea. So I've got the imbalance in the entropy being satisfied by the entropy, the dissipation, divided by sort of the average temperature in the interior. And I can then rearrange this to give me the dynamo power or the dissipation in terms of the heat flow that I'm putting through the system. And this ratio of temperatures is what we refer to as a Carnot efficiency. It's the classic Carnot efficiency that tells me how much of that energy am I able to use to do useful mechanical work. That's the idea. And so, yeah. Oh, okay. Yes. So that's a constant heat flow. So it's only a good. It's only linear if that's constant. That might not be constant. And I would guess I'm going to argue that if that heat flow was constant, and we go back to these early times, we're out of business. And so if we have a field at 3.5, I don't think that can be the heat flow. So, but you're right. That's just really for illustration more than anything else. No, I won't go there. It's a funny story, but it's only funny if you have lived through the history of the story. Okay. So here's just sort of a very minor, in some ways, a very minor extension of that simple Carnot efficiency idea. You know, we've got the dynamo power illustrated here, and we've got a bunch of different Carnot efficiencies. We've got one here associated with the thermal convection. So this is secular cooling and radioactive heat production, in essence. And what you'll notice, and you can see what its value is here, at least for typical core properties, it's about 10%. Okay. And what you'll notice is that this heat flow that I'm multiplying by the Carnot efficiency is the CMB heat flow. That's the mantle, what the mantle is doing, minus the fraction that's conducted toward the boundary along the adiabat, right? So it's only when I get up above the adiabatic heat flow that I start getting these boundary layers, and I actually am able to do mechanical work. And so this will tell you how much mechanical work I do by that process. Here's the one associated with the latent heat. It depends on the CMB heat flow minus any radioactive heat production in the core, because you don't get inner core growth and therefore latent heat release if you're not cooling, because you don't grow the inner core if you're not cooling. And so it's only the amount of heat flux in excess of the radioactive heat production that drives this term. And then here's the Carnot efficiency for the compositional buoyancy. And it also depends on the difference between the CMB heat flow and the radiative, or not radiative. I give 0 marks for students that get radiation and radioactivity wrong, so I'll have to be careful. The radioactive heat production in the core, okay? Again, connected with cooling. And you can kind of see what these things, these Carnot efficiencies do as a function of radius. You know, latent heat increases as the radius gets bigger. The chemical efficiency goes up, chemical buoyancy efficiency goes up. This is the present radius of the inner core, whereas the thermal one is more or less constant because it's really determined by stuff going on at the top boundary. Okay. So the point here is that as we go back in time, right, and the inner core gets smaller, we're losing latent heat effects, we're losing compositional buoyancy effects, and we're leaning on the thermal buoyancy completely to drive the dynamo. By calculations that I haven't explained. So I could do it either by a very straightforward extension of the entropy arguments, that I described. Exactly. But just worrying about all of the sources of entropy. Or I can also get this from just thinking about buoyancy fluxes, and I'll get exactly the same answer. And I've been told by many that the entropy argument is much simpler. And I guess I've come around to that a little bit, but you can get them either way. Okay. So I would say that the thermal history, the models for the thermal history, and I would even claim that these Carnot efficiencies are relatively uncontroversial. I don't think that there's any debate about how we go about calculating these things. There's plenty of debate about what parameters to put into these calculations, but the underlying description I don't think is controversial at all. Okay. So here's just a sort of simple example with that 6 terawatts of heat. We could drive or power a dynamo today with 6 terawatts of heat in the present inner core radius of maybe about 1.3 terawatts. That's a pretty decent field by standards of the numerical models, at least. And we could even power a fairly wimpy field in the early Earth based on thermal buoyancy alone. This number is based on the thermal conductivities prior to these recent studies. If we think about thermal conductivities that are a factor of 2 or 3 higher, then suddenly the present day power goes down to about maybe 0.8 terawatts, and the early Earth just doesn't work at 6 terawatts. So in some sense, it can't be right. Okay. So let me just digress just for a sec, because I want to put together a very simple thermal history model just to show you kind of the issues that are at play in thinking about whether or not a field existed in the early Earth, what it requires, could the field have disappeared and come back again. I just want to digress a little bit, going back to this figure that you saw earlier in the mantle convection story. Okay? So we said before that the convective heat flux, we represented it in terms of this sort of contribution that we would get by conduction, and then scaled up by the Nusselt number, and then here I've substituted in that Nusselt number, Rayleigh number relationship. And so if I take my Rayleigh number and I stick it in there, I've got a L cubed, then to the 1/3, and I've got an L down here. So the L dependence of this heat flux completely disappears. It gets removed from the solution. And the usual way that this is interpreted is to suggest that the stuff that's going on here, the sort of processes that are going on up here that determine the heat flow, don't really know or care about the stuff that's going on down here. And so if I were sort of walk through this sort of exercise and sort of figure out what the convective heat flux would be, it would depend on some constant, which would be these various material properties, times T to the 4/3. So there's a T right there. There's a T to the 1/3 right there, so that gives me my 4/3. And it's often assumed that because of this independence of the depth, the fact that this boundary is operating and this boundary is operating, and they really don't care about each other to some extent, that we could think about parameterizing this model in terms of just the temperature jump across the boundary layer and the temperature jump across the boundary layer there, and treating them separate. So here they're equal, and so we can figure out what that is, but if we were to allow the system to evolve from these being symmetric, perhaps we could sort of characterize these in terms of just the temperature drop across the boundary layer to the 4/3 power. So that's something that I'm going to do to characterize the heat flow that's coming out the bottom of the mantle. Okay, so this is going to require a little explanation. Is a thermal dynamo on early Earth possible? So for this, here's the picture. I've got my mantle, I've got the core, I've got some heat flow coming out the top, which is governed by the state of tectonic style, whatever that might be. I've got the CMB heat flow coming across the boundary here. And I'm going to take this heat flow and divide it into 2 regimes. So the heat flow will depend on the temperature in the mantle, and there are going to be 2 regimes that I'm going to assume. One is a so-called pre-tectonic model. This is something from Norm Sleep's review article, and this review article, for those of you who've read it, you'll know that this is a review article that contains probably about 60% original new material. That's Norm. It's a very nice article, and I recommend it to everybody. He used the word mush ocean, and so it's too confusing with magma ocean. So I'm referring to it as pre-plate tectonics, and he has an estimate for the heat flux that you'd expect as a function of the mantle temperature. And this would be a model that would sit in between the plate tectonic and the magma ocean regime. I think it involves a lot of heat transport and heat being carried by melting and latent heat and such. And so I'm going to just take this as an example. And it's going to apply to the case when the mantle temperature is above 1,500, potential temperature is above 1,500 degrees C. And then for the plate tectonic regime, which will occur below 1500 degrees, I'm just going to assume a constant. Probably not true, but we're only going to look at sort of the early evolution of the planet after it hops into this plate tectonic state. And so for the sake of simplicity, I'm going to just assume that this is constant and allow the heat flux across the core mantle boundary to be this sort of classic delta T to the 4/3 power. Let's just sort of see, just as a representative example, what comes out. Okay, so we've got the divide here. So there's regime 1, the pre-plate tectonic regime here, and we're getting rapid cooling, very, very efficient cooling during this period. And then we sort of go into a plate tectonic regime, and here's the heat flux that I'm imposing for that plate tectonic regime for this early part of the evolution, 76 terawatts. So not quite a factor of 2 higher than the heat flux that we think is appropriate for the mantle today, but substantially higher. Okay, yep.
It looks like you're heading at 3 billion years to a mantle temperature that isn't that different from today's mantle.
Yeah, so this is obviously perhaps too high. That's very possible. So you're thinking mantle temperatures here about, you're thinking about mantle temperatures about 1350, right? Something on that order? But all the way over to here somewhere, yeah. So it has to slow down a bit. Yeah. But let's just sort of see what the consequences of assuming this number is. So if I look at the heat flux that's coming across the core mantle boundary, of course, during this region where the mantle is very vigorously convecting, I'm getting prodigious amounts of heat flow coming across the core mantle boundary. My guess is that there's absolutely no trouble powering a dynamo during this early phase. It seems very likely. In fact, in some ways, the convection could be so vigorous, the effects of inertia could become so important that actually might be not as rotationally dominated as we conventionally think it is. And it's even possible during that early vigorous state that the field might not be dominantly dipolar, which would be relevant for this issue of nitrogen isotopes on the moon, because the dipole part is the part that's strongest further out, and it's going to be providing most of the protection against the solar wind. But then, okay, we switch to this plate tectonic regime. The heat flux across the core mantle boundary is relatively low here now. It's sort of a little bit before 4 billion years. And what's happening? At constant heat flow coming out the top, what we're seeing is the CMB heat flow is gradually increasing. And the reason is because for this heat flow, this is getting, how should we say, the radioactive heat production in the mantle is getting lower and lower and lower relative to this value. And so that allows more cooling of the interior, and so that allows more heat to be coming out of the core. And so as the radioactive heat sources gradually cool off, we actually start to increase the rate of cooling of the mantle and increase the heat flux across the core mantle boundary. And so if you thought that you need a field at 3.5 and thermal convection is the only game in town, then if 5 terawatts of heat across the core mantle boundary was enough to do it, you could sort of switch on a field here and have some brief period where there was no field. But I guess the more important point I want to make is just simply that the values that we assume for these heat fluxes have implications for the amount of heat that's coming out of the core. And it's really the total heat flux at the top relative to the amount of radioactive production that's taking place at that particular time that's ultimately going to determine the CMB heat flux. And so I had said that both Korenaga's and Norm's estimate of heat flow at these temperatures of sort of 14 or 1500 degrees or so were probably too low to get a dynamo, and that's essentially what I meant, that they're just not high enough heat flows to get big enough heat flows coming out of the core to drive the whole story. Yeah.
Maybe you have explained it, but I haven't understood. What makes the transition?
Oh, this temperature. So I think in Norm's model, I guess the idea is that the volume of melt that you get below a mid-ocean ridge falls below some threshold that you transition to a different style of convection. In some ways, it's completely arbitrary, but that's the idea.
So the radio transmit, it doesn't make any assumptions, right? It's gravity.
Yeah, that's right. So this is but in some sense, this would be analogous, if you continue this, and Mark was talking about this, right? You could imagine a situation where as you cool even further, the amount of melting that you're getting at a mid-ocean ridge drops below some certain fraction, and the ridge locks up. And so now you're into a new regime. And so it could well be that you transition to a different style of convection over a relatively narrow range of temperatures. In this model, the 1500 is I think, largely arbitrary. But it's the physical motivation is that you have some large volume of melt, and actually the melt transport in the ridge area is actually really important in getting the heat out, basically, is the underlying assumption. Okay. Good. So let me just, I'm going to finish at 12 o'clock, actually, so you'll be all glad to know. I wanted to just make a couple of comments about dynamo models. And, I sort of, in some ways, we've had this sort of, almost like sort of an AA meeting, right? Sort of where people confess all the sins of their field and want to reveal this. And I guess I'm doing the same thing here. My original plan, to be honest with you, is to sort of show you how these flows produce these sorts of fields and turn you all into card-carrying dynamo modelers. And so I have shied away from that a little bit. And what I want to do mostly is just give you a sense of, A, the models have been great. But there are some real serious challenges. And I'm going to make the claim that probably isn't widely held, but it's very possible that we could see a complete revolution in the way in which these models work. And I'll try to explain what I mean by that before 12 o'clock. So these are results from a couple numerical models. This is a numerical model postdoc that has been doing with me, Hiro Matsui. And these are a field model that was done by Gary. So these flows didn't produce that field, but similar things are going on in both these models. He makes really nice field models, and Hiro makes really nice flow visualizations. And so the merger of the two. This is definitely a rotating fluid. And what you're looking at here is vertical vorticity. You don't know what that means perhaps yet, but you're going to. And what I want to emphasize is the fact that these flow structures seem to have an elongated structure in the vertical direction. So they're very elongated in the direction of rotation, and it seems like there's a short length scale in the perpendicular direction. And these flows are really, really efficient at generating magnetic fields. We think that rotation is important, and we think that rotation is important because it gives rise to this style of flow, and that style of flow is important in generating magnetic fields. Okay. So here's a brief statement of the problem. Conservation of momentum, going back to Isaac Newton, that's just Newton's law, right? And we talked about that in the mantle convection problem. It's the same description here. Energy conservation, arguably attributing that to Fourier. I guess we could debate that. For the temperature field, and then the magnetic field, based on Maxwell's equations, tells us something about how the magnetic field evolves with time as a function of the fluid velocity of that conducting material, its electrical conductivity, and the field that presently exists. Okay. It turns out that in the approximation, sort of the low frequency approximation that we use, all the pieces to do this existed before Maxwell's equations. So we don't really, so in some ways I could put maybe Faraday up there perhaps instead. Okay. But one of the things that we do worry about a lot is the fact that the coordinate system is rotating. And so by comparison with mantle convection, we actually worry about the fact that the fluid is rotating so that the reference frame is not inertial. And so when you have your accelerations, which are written here, additional terms, sort of pseudo-forces, arise because of the fact that you've chosen a non-inertial frame. You get the Coriolis Force, which is this guy right here. You get some centrifugal accelerations, which are related to, or can be described in terms of the gradient of potential. And all of those things just get absorbed into the pressure. So you see that disappearing. So what have we got? We've got our accelerations here, the Coriolis Force really being part of those. Pressure, our buoyancy that's driving the flow. And here's the viscous effects right here. Exactly the same as the mantle convection problem. Does anyone actually, almost cruel to do this on a Saturday morning, but does anyone know why mantle convection people never worry about this force? You know, it's funny, the mantle convection community makes a big deal about tossing away these guys. You know, this is infinite Prandtl number convection. Look at how small the inertia is. And you almost never hear about the Coriolis force, which is orders of magnitude bigger than this. But it's still okay for mantle convection people to toss this away. And the reason is that this viscous term here is gigantic, okay? And so this term is really, really small compared to this term in mantle convection. And so we can just get rid of the whole kit onto that side. And of course, the buoyancy is the thing that produces those flows. So these guys have to be comparable. And almost by requirement, this must be comparable to that. So we can look at the core case and ask the question, well, how big, roughly speaking, are these terms? So we can think about, well, how big is the viscous term compared to the Coriolis term? That's this guy right here. It depends on the ratio of a bunch of parameters, viscosity, rotation rate, the length scale, which almost always is the radius or the shell thickness. And it's about 10 to the minus 16. So viscosity is utterly negligible, at least in the bulk, in these calculations. And also inertia. if I looked at sort of the magnitude of this term, for example, compared to the Coriolis term, it's really small, 10 to the minus 7, maybe even a little bit smaller. And so when you hear dynamo people talking about Ekman number, what they're actually talking about is this ratio of forces. So Ekman number translates to the viscous effects relative to other important things. So this is the Ekman number, and this is often called the Rossby number, and it's the importance of inertia to Coriolis. And Dave in his Chalk Talk made the comment that Venus is rotating slower than the Earth, but it's not a problem. And he's absolutely right, because look at how small this number is. If you made this rotation rate a factor of 100 times slower, this is still 10 to the minus 5. It's still a small number. It's still rotationally dominated flow. And you're still going to get the kind of structures that we need to generate fields. So the rotation is absolutely not an issue in Venus. Yes? Yes. Okay, so right. So the estimate that goes into here is an estimate that has come from first principle calculations. It's not very different from the viscosity of iron at ambient conditions, and it's actually a little bit less than water. And this is something of a surprise to some people when they hear about this, because they think about, lavas erupting out of the surface, these sort of thick flows. But here, really, the viscosity we expect to be comparable to, or perhaps even less than water. So the thought experiment is, put on your safety gloves, put your hands into the core, maybe goggles too, and you lift the core material up and it would just simply run through your fingers like water. It's very, very low viscosity. And well, that's the thought. There are some arguments that suggest that pressure is important. I think that this represents a fringe of the but not completely impossible, I would say. But there's really no compelling evidence to suggest that the viscosity increases substantially with pressure over the range of pressures that we're talking about here. Okay, so let me just make one comment. Let me just step back for just a sec. So you might be plausibly arguing, look, this is 10 to the minus 16. If I drop this off and I carry 16 places of digits of accuracy, only at the very last digit am I going to see this guy assume. Surely I can get rid of this, right? And even the inertia, 10 to the minus 7, I don't know whether other people, mantle convection people, would say that, yeah, I trust my calculations, the 7 significant digits. I don't think so. And so, this term seems pretty small too. So you might think about how far you can go by just sort of keeping the big guys in the force balance and seeing what happens. And so that's what I've drawn here. Here's the momentum equation. Here's the force balance, momentum equation, Coriolis, pressure, gravity, buoyancy effects. And Michael introduced the concept of vorticity. It's just the curl of the velocity field. And vorticity is your friend if you're going to do any kind of work with low Reynolds number flows. It's the absolute, I would say, essential mental crutch to think about how these things work. If you take a momentum equation for a velocity field, to get this into an equation for vorticity, you just take the curl of that equation, right? Instead of velocity now, I'm dealing with vorticity. And this is the curl of this piece. Okay? And so I've played a little bit of games. This is very straightforward. You guys can do this. This is sometimes called the thermal wind equation. And it involves velocities and the gradients of the densities and all that kind of thing. But if I look at the radial component of this equation, sort of the g component, if you will, I get this equation right here. So this piece drops out, and all I get is this, and I have the radial velocity. So in words, what this says is that the gradient in the velocity in the direction of the rotation axis is 0. So it does not vary in the direction of the rotation axis, which is consistent with all of those elongated convection columns that you saw in the numerical models. But it's even more interesting, I think, than that, because the radial velocity at the top and bottom of the containers must vanish, right? We don't have radial flow going out of the container. So not only does it not vary, the radial velocity is 0 everywhere. If you have a fluid that has 0 radial velocity, even if you have buoyancy in it, then that's telling you that buoyancy is not rising. So you put a buoyant parcel into a inviscid, rapidly rotating fluid, and it just sits there. It doesn't rise. Right? Yes. So the meaning of those colors were just the sense of rotation, whether the vorticity was... So here's the vorticity vector. You can imagine sort of a swirl going around like this. So those different colors were whether the flow is swirling clockwise or counterclockwise, essentially. Sort of the vertical vorticity, but which direction is it pointed? Does that surprise you? actually. Buoyant parcel, put it in the inviscid fluid, it just simply sits there, doesn't rise.
Does radial here mean away from the rotation?
So radial means here in the same direction as gravity, basically. Yeah. And I don't care about the sign of it. I could define it radially outward or radially inward, but just the radial component of the vector. So in other words, in the direction of g. So there would be no buoyant parcels rising radially up through the fluid, even though they're buoyant, or sinking down through the fluid if they're dense. This is why you have to love rotating fluids, I think, or one of the reasons why you have to love rotating fluids. There is a good physical explanation for this, and if you were curious, we can talk about it later. Let me just go back. So if we do the obvious and get rid of the small things, we're out of business. So either we have to add inertia or we have to add viscosity. Inertia would be the sensible one to add because it's the bigger of the forces, but if you're thinking about onset of convection, you're starting from a static fluid, then these nonlinear terms, products, are going to be pretty small. And so to get convection kicked off, we're going to have to rely on, at least in this case, viscosity to do it for us. And even though it's very small, this is how it works. And so let's go back, add that piece. Okay, so we've added the viscous force. We take the curl, we get this equation. We look at the radial component, and instead of being 0 now, we have some term that depends on the viscosity, which is very small. We can make order of magnitudes of these quantities here. We expect, because the radial velocity doesn't change very much with depth, it's still going to be almost invariant, but not varying very much. Its appropriate length scale is probably the thickness of the shell. Whereas we're going to need some really, really thin, fine horizontal length scale so that we can make viscosity important enough to actually make this balance. And so we could rearrange this equation for the length scale, and here it now is in terms of the Ekman number times the length scale, but the characteristic dimension is about 30 meters. So convection should start in the core by having these very thin helical convection columns that are maybe 30 meters thick and 3 times 10 to the 6th meters long. I would be really surprised if that was stable. And so certainly some inertial effects are going to come back into play. But let's just sort of look at, I've gone backwards, sorry. So let's just show a numerical simulation. This is at an Ekman number of 10 to the minus 5, so we're still 10 orders of magnitude away or something like that from the Earth's conditions. And we consider this good. This is a good solution, basically, relative to some. And all it's going to do is, it's not a simulation, it's just simply going to show you, wonder why that, isn't that funny? Oh, there it goes. Okay, it's just being very slow. So I had coffee, but the computer maybe didn't have coffee. That's curious. Should be working, but it's not. Oh, there we go. Okay. What you can see here, I think, this is vertical vorticity again, so this is kind of the swirling motion one direction or the other. You can kind of see pairs of these things, either with one sense of rotation or the other. They're very thin. Try that one more time. There we go. You can kind of see these in pairs often. Very, very thin. The spacings here is essentially set by this Ekman number. So the spacing between these guys is probably on the order of Ekman number to the 1/3. Okay. So, and again, we're very, very far away from being in the realistic conditions. We really want this number to be down around 10 to the minus 16, 10 to the minus 15 or so. So we have a long way to go. And the problem with the numerical calculations is you make that Ekman number smaller and smaller and smaller. This lateral scale gets finer and finer and finer, and the resolution that you need in the calculations to actually capture that feature get really, really difficult to do. And so numerically, we just can't go there. We can't get there. And so So the tangent cylinder is a separate issue. Yeah. Tangent cylinder, it's harder to see here, but you do get a sort of a shear layer that develops around the tangent cylinder that kind of isolates what happens inside the tangent cylinder from outside. And the characteristic length scale of that transition layer is of order the Ekman number to the 1/3. So a very thin layer as you move in. And it tends to impede flow. I mean, one of the ways that you can think about the tangent cylinder is in terms of vorticity. Vorticity, let me just make this one quick comment. So vorticity is a property in a fluid, if it's low viscosity, it's kind of like frozen to the fluid. And so imagine taking a parcel of fluid which is on the inner core and connects to the top of the mantle, and as I move it toward the equator of the inner core, it starts to get stretched, right? And stretched, and as I get really close to the equator, it gets stretched infinitely fast. A rapidly rotating fluid doesn't like that to happen to it. And so that's a tendency to resist moving off of the inner core if you're on, or being on the outside and moving on to the inner core. It's that sort of stretching of those line elements that a rapidly rotating fluid really resists. And so it tends to sort of separate the flows into separate regimes, even though there's no physical hard boundary there to prevent it. Yeah.
I think the color of the intensity of the vertical magnitude of the vertical vorticity.
Yeah, this is the vertical.
The direction, the vector of the vorticity, are they still aligned in the vertical direction?
Yeah, it's just simply the fact that if it's pointed in a positive z direction or negative z direction, it just gets these different colors. So what you tend to get, let's say, a cyclonic flow right next to an anticyclonic flow. And they're not really columns per se. They're more like sheets, aren't they? I don't know if you've noticed that in the simulation, but they're more sheet-like than column-like. But it's essentially just sense of circulation is going clockwise in one of these guys in blue, and then the yellow, it's basically going in the opposite direction. And they're generally associated with upwellings and downwellings. So one that spins one way will be associated with upwelling. One that rotates the other way will be associated with downwellings. Okay. And it's the way that the convective system gets organized because of the rapid effects of rotation.
So the CIDER pattern in this figure means there is a cylinder.
Yeah, so Doug's question was, there is sort of this notion that you often hear in the literature about the tangent cylinder, and it's a cylinder that basically is tangent to the inner core at the equator and basically goes up and sort of encloses. And the dynamics inside the tangent cylinder, sort of inside this region versus outside, is quite different. And the point, I guess, is that the structure of this boundary essentially makes it difficult for fluid that's in here to move out and for fluid that's out here to move in. So it almost looks like an invisible but almost impermeable boundary from the point of view of flow. And so all of these flows that we're looking at here, all of these are mostly outside the tangent cylinder.
I'm also wondering whether the velocity of the fluid is also comparable to the electric current. We know that the magnetic field is proportional to the vorticity of the electric current, right? So the velocity of the magnetic field will be the same as the velocity of the
Velocity.
current.
Yes, that's correct. But it's not necessarily true that the velocities have a direct correspondence with the complexity of the currents. That's true. And that's actually a point that I'm going to make. Right. Yes, it's funny, we almost never think about currents. That's not completely true, but we don't think about currents very much, and we definitely don't think about electric fields very much. I sort of sometimes wonder if there's ways of casting the problem that would make it easier for the numerical models to work versus others. And me personally, I haven't been able to come up with an alternative over the standard magnetic induction equation, which is sort of the ensemble of all Maxwell's equations collapsed into a single equation for the magnetic field. Okay. So are the models realistic? So here's the dirty laundry. So you saw that we can't get to the realistic Ekman numbers. That's a real struggle, and that's one of the problems. And so there's been a general sense that, well, we'll do the best we can. We'll make the Ekman numbers as small as possible, and then just simply use scaling relationships to go to where the core is and make inferences. And there's a popular scaling which is based on the assumption that because the viscosity is so small, surely it must be unimportant. That ultimately, whatever the core is doing, it must not really care about the viscosity very much in detail. And so it turns out, for that particular scaling, implicit, not explicit, but implicit in that scaling, is the assumption that the inertia plays an important role in breaking what I described as the Taylor-Proudman constraint. It's the thing that allows convection to happen. And it makes sense in a way, because that's sort of a much bigger force, probably, than the viscous effects. And so what's being shown here is a plot of how that length scale how we would expect the convective length scales to vary with this sort of Rossby number, that's the measure of the inertia, as a function of that value. And so this is the theoretical prediction that you would make if inertia broke the rotational constraint. And these are the results that come from the numerical models as a function of Rossby number. And what's shown here are just the different values of the Ekman number that were assumed in the calculation. So Ekman number is something that you can specify because it only depends on physical properties. The Rossby number is something that you have to extract because it depends on the velocity. So this is a calculated quantity. This is an input quantity. And so, I don't know, we can sort of compare geochemists versus geodynamics. Is that a good fit? Is that line a good fit? I don't know. I don't think so, personally speaking. And maybe even more suspicious, perhaps, is that there is a trend, clearly, between Ekman number, as you go through, all the red guys are up here, all the blue guys are down here. And so it does seem, at least in the numerical dynamo models, that they are not obeying sort of the length scale does not obey the underlying assumptions of the scaling relations. On the other hand, if you make the assumption that the models are viscously dominated, what the length scale is controlled by the viscosity of the fluid, and you do the same kind of plot, so now length scale is a function of the Ekman number for a bunch of different Rossby numbers, what you find, I think, is a better plot, maybe not perfect, but you also see representatives of the different values here. And so there's not as much systematic trend as you see here. And so it appears, at least in the dynamo simulations, that the structure of the flow is being completely controlled by viscosity. And so it's very unwise, I would suggest, to take those calculations and use scaling relations that rely on the assumption that viscosity is unimportant to then extrapolate to the core.
You haven't talked about the role of the Lorentz force.
No, I haven't. You're absolutely right. And the Lorentz force is another force that you can bring to bear to actually break the constraint. And the normal assumptions for the magnetic field is that it's kind of independent of scale. So that if you had a field, it's being distorted by the flow, that will provide a force that breaks this constraint, and it's an alternative to assuming inertia, and it's an alternative to assuming viscosity. And the usual assumption is that the length scale of the flow would be of order L, some constant, perhaps 0.2, 0.5, 0.3, 0.1, whatever. What you can see here is systematic variation in the length scale with E. And so it's pretty clear that these dynamo models, their length scales of convection is not being set by the Lorentz force, but it's being set by viscosity. Yeah. So that is a very good point. Okay, last slide. Maybe 5 minutes over. I made the comment during coffee that because I have the last talk, I'm almost certain to have the oldest reference paper of Leonardo da Vinci. After the mantle convection talk, Louise Kellogg came up to me gently and sort of said, when you tried to give Richardson's poem off the top of your head, you really did butcher it. and she was quite right. And so I thought that I would just repeat it here because it's relevant for what I want to make. And the quote is, big whirls have little whirls that feed on their velocity. Little whirls have lesser whirls, and so on to viscosity. And so this notion of this sort of inertial cascade down smaller and smaller and smaller scales, eventually arriving at viscosity, which limits the spatial scale of the flow that you would expect. And so this is Richardson's. It's sort of an adaptation of an earlier poem. Here's a picture of Leonardo da Vinci of water being poured into a tank. You can see the big swirls going to little swirls, going to little swirls. It's the same thing. This is the graphical picture. This is the more poetic picture. But the point is that viscosity, or you could think of it as a momentum diffusion, ultimately limits the scale of the flow, right? You would expect the structure to be ultimately governed by essentially viscosity. You can have bigger scale structure, but ultimately at the small scales, this is what limits the scale of the flow. And similarly, magnetic diffusion, which depends on electrical conductivity, limits the scale of the field. Okay? And in all of our numerical models, we tend to use values which are not very much like metals. Metals have viscosities relatively low, 10 to the minus 6 meters squared per second. Thermal diffusivities perhaps a little bit bigger, but the magnetic diffusivities are of order 1. And so if we start thinking about what the length scales would be, we would expect that because the magnetic diffusivity is pretty big, that as the magnetic field reaches the diffusion scales, that limits how small they can get. Whereas the velocity scales can get much, much finer scale before viscosity kills them off. And so we would really expect a difference in the scales of the fields and the flows with these differences in properties. And so in metals, the so-called magnetic Prandtl number, the viscosity, think of this as the scale of the velocity field divided by the scale of the magnetic field, is tiny, 10 to the minus 6th. Our best models, when models first came online, the ones that produced the most Earth-like fields had magnetic Prandtl numbers of sort of 5 and 6. In other words, viscosity bigger than the magnetic field. This produced nice, smooth velocity fields, big scale velocity fields, which could amplify the field, and they worked the best. And it tended to be, as you made the magnetic Prandtl number smaller, more like metals, the solutions got less like Earth-like models. And you can actually see this in numerical simulations. We haven't gone very far, but here's a calculation of Ekman number 10 to the minus 6, again, still roughly 10 orders of magnitude away from where we are. But now this magnetic Prandtl number, 0.1. So we only have to go from 1 or order 1. We've gone down a factor of 10. We need to go 5 orders of magnitude more downscale. But look at the difference. Here's the velocity field. You sort of see those sheet-like features. So this is the radial flow. It's associated with the same structures. Okay. Here's the magnetic field. Similar pattern, but the scale here is clearly much bigger than the scale here, right? And so again, in our numerical models, we really want to push this number down about 5 orders of magnitude more, and the sort of scale separation that takes place here is going to be extreme. And so, to be honest with you, I don't know that we're ever actually going to get there. Whether this is the right, I'm not sure that this is the right way to go. And so just in the last 2 minutes, very briefly, I have thought that maybe instead of fighting this trend, right, instead of saying, look, we just make the flow smaller and smaller and smaller, maybe we go to this limit. We say there really is scale separation. The flow is very small scale, and the field is very big scale relative to that flow. And let's explicitly incorporate those ideas into the models. And it's just a very different way of coming at this problem. And the rationale partly is that you can do numerical simulations in a little box like this and actually use realistic properties, maybe 10 kilometers, something on that. You can impose a magnetic field, but the idea is that a little box like this is seeing a constant magnetic field, because the magnetic field is just so much bigger scale. You can run numerical models. This is an example of what the temperature profile would be in one of these little boxes. Rotation vectors here, the gravity vectors coming in at sort of 45 degrees. You see no evidence of the direction of gravity in these temperature fields, I would say. But you do see elongated structures in the direction of rotation. You see elongated structures in the direction of the magnetic field, and very, very fine scale across this. What's remarkable, actually, Dave, do you know what sets the scale in that? You couldn't guess, but it could only be one of two things. It could be viscosity, which it's not. It's thermal diffusion. Thermal diffusion is what ultimately limits the scale. The viscous dissipation in these calculations is virtually zero. Okay? But the point here is that I think by sort of doing these calculations, starting at the small scale, looking at how the small scale interacts with the field, I have a thought that we may be able to sort of build up numerical models by explicitly taking advantage of this scale separation, as opposed to pushing global numerical models all the way down. So I have in my works, the works at least, a revolution is planned, and if it never pans out, you'll probably never hear about this again. If it's successful, then you'll all know about it, and you'll remember this day. Okay. So maybe with that, I'll just summarize and say that I think from the point of view of your projects going forward, I think that the issue of the magnetic field is important because it does provide a constraint on thermal evolution. And one of the questions that you have to ask yourself for any mantle model that you come up with, does it provide the heat flow across the core mantle boundary that's required to drive a dynamo? And the one caveat, I guess, that I would attach to that is that I think it's still possible that chemical variations, chemical exchange between the core and the mantle may still play an important role in terms of providing additional buoyancies to get us out of some of the problems that have arisen with these much higher values of thermal conductivity really in the last just a couple of months. With that, thanks. So I'm happy to take questions, obviously, but if you guys want to go, I won't be offended. Yeah.
There's the Holding at Home project where computational biologists
Right.
are getting desktop computers around the world to compute
Yeah.
molecule behavior for them. Is there any hope that a project like this could help, or is this simply viewed beyond the scale of computing power?
You know, the answer is to do the problem correctly, I think, is beyond hope. I used to joke, I remember, that there might not be enough silicon on Earth to make the memory that's required to store the solution that you do the calculation with. But I think the other point is that it's a very, these are tough calculations in the sense that all parts of the flow are interacting with all parts of the flow. And so, I have a little bit of current here. It generates a magnetic field, and that the influence is non-local. And same with pressure. And so all parts have to be talking to all parts. And so the problems that are most useful for community involvement will be ones that paralyze very easily. But ones that sort of have very tight communication between all parts, I think becomes a real challenge. And so, to be honest with you, I don't know what the solution is. We've been working on trying to get better turbulence models. We've been trying to do better than sort of eddy diffusivities. And there's some progress. I think we're going to be able to push Ekman numbers and Prandtl numbers maybe an order of magnitude or two, but we're not going to go all the way. And so it just occurs, to me at least anyways, and I may be the only one, but this notion that the scales are probably going to be very, very separate at the actual conditions, and that maybe we need to be thinking about doing it differently, smarter, exploiting the things that we actually know, rather than just simply trying to brute force a numerical model to go where it doesn't want to go. That's, yeah, Vern.
What do you think of the utility of collapsing the problem to two dimensions like Kalman's does?
Yeah, right.
At least to get ideas of heat transport things.
Yeah, I guess it is. I mean, yeah, I suppose it is, although what you recognize here with these calculations, for example, is there's a lot of vertical structure. There's not. And so I suppose the question is, if you toss out that vertical structure, the structure that's aligned with the rotation axis, do you lose something important? My guess is that you probably will. But I mean, there's been a lot of work done with these sort of quasi-geostrophic models. They can go to much higher or much lower Ekman numbers. They can be much more realistic. But I worry a little bit that you may be throwing out a lot of the field generation that's going on in the interior of those flows, because you can't really, I don't think you can really quite get well, I should caution, it's going to be difficult, I think, to get realistic dynamos with those sorts of flows. That's my guess. Yeah.
So in the simulation of Eric's work, I think he includes the form of the magnetic.
Oh, absolutely does. And these numerical models that I showed, actually, these comparisons of numerical models also do that. So, when I show these results, the Lorentz force is in there, basically. So these guys, if the Lorentz force was dominant and it was scales the way that we think, what we would expect is once we get to that state where the magnetic field is the key arbiter in breaking the Taylor constraint, we would kind of expect this length scale to be nominally independent of viscosity. And clearly it's not. So it's in there, and if it was able to do the job that it's often been ascribed to do, and maybe even does actually in the core, then you would see these as constant. And all I guess I'm saying here is that viscosity is breaking the constraint. And so you want to be a little bit careful when you take numerical calculations in this regime and then extrapolate them to a regime which seems perfectly plausible, but which we have no representative members of the ensemble of solutions that we're doing to do that extrapolation.
So he doesn't include the weight constant.
Oh, yeah, yes, he does. Everybody does. I mean, you can't get numerical solutions without them. There's been efforts to try to do that, and so far not successful. You lose some important physics, actually, when you toss away viscosity. Stuff happens at the boundary layers that is not just simply local to the boundary layers, but which is really global. And so you kind of need it, but the viscous boundary layers, the mechanical boundary layers, might only be 10 centimeters thick for realistic viscosities. Yeah, Rick?
Most of your discussion is based on the idea that heat flux out of the core is homogeneous across the whole course.
Yeah, that's right.
But we spent a lot of time talking about how well heat.
Yes, right. So,
Different temperatures.
yeah.
Different patches.
No, that's a good point, Rick. That's a good point. And so the energetic calculations that I showed are really intended to be integrals of that heat flux. And so when you think about it from the point of view of energy balances, or you think about it sort of entropy fluxes, these are really integrated properties. And so if the average heat flux is this, then this is the amount of power that's available. Of course, if you have lateral variations in heat flow, then it's going to have a profound influence on the style of flows and the way in which the dynamo actually delivers those expectations of power. And so you're absolutely right. But if you've got the integrals right, then the integral properties are probably okay too. It's just the style of convection, perhaps we see evidence of persistent features in the field going back even 5 million years that don't seem to average away when you average the data. And so that's clearly telling you that there is some persistent pattern of flow at the top of the core, probably related to lateral heat flow variations that are producing kinks and bumps in the field that we observe in paleomagnetic observations that aren't going away. Because, if this was rotationally symmetric, you think if you just waited long enough, like the axial dipole, you just wait long enough and you basically get a dipole. You wait long enough and all that zonal or structure that varies along lines of longitude would go away. It doesn't. So clearly, there's nothing in the core that would argue for such persistence, and almost certainly it's got to be the mantle's imprint on those flows. Yeah. So I would say kind of the beauty of the global things is they don't really care about the details. You get the bulk energetics right, and it has to deliver. Then in detail, how it does it is up to the core.
Aspects of this question may have been answered already, but so you showed this momentum equation and that there's this span of scales of 16 orders of magnitude or something like that.
Yeah.
We have to keep all the terms to get the physics right. And now numerically we are maybe a third of the way or halfway down.
Okay.
Right?
Well, we're maybe a third of the way, yeah.
So
we're still like 10 orders of magnitude away is how I would prefer to describe it. Yeah, and we feel pretty good about that, right? I mean, I'm definitely downplaying the importance of these solutions. I mean, these are heroic efforts, right? And Gary will run a simulation and he'll report the results a year after he starts that calculation. These are long integrations, but the problem is that they're still very, very far away from Earth-like conditions. And so my concern only is that so they're great proof of concept, right? We sort of get the idea of how the flows are organized, and we get a lot of insights. But I have the feeling that we're not in the regime that we need to be in to be making inferences to the Earth and having them be meaningful or sensible, I guess. And so that's my bias. Now, there'll be people in the community that will completely disagree with me on this. They'll say, you're wrong. Like Uli Christensen once said to me, he says, yeah, I used to worry about that, but I don't anymore. And his argument is that the details of the parameters are not so important as long as you get them wrong in the right proportions. To me, that is, by definition, an optimist, right? Because there are so many ways that things can go wrong that to get everything wrong in the right proportions and somehow the right answer comes out, maybe, right? But I would be really surprised. So I guess I'm a pessimist and Uli is an optimist. And both are perfectly legitimate points of view because we are not in a position to be able to argue that one or the other is incorrect at this stage.
You actually answered my question.
Okay.
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 I guess my other question was, what are we not explaining about the physical properties of the core that we observe?
The field models, in some ways it's unfortunate, in my opinion, that the field models have been so successful at producing dipolar fields, producing time variations in the fields, that you can go to the observed record and actually make these connections. And it looks like it seems reasonable. But I guess that I would say that very often the way you get more Earth-like fields is by moving the parameters in the opposite direction toward the Earth-like values. And so that's, again, Uli would say that it's more complicated than just doing this, to doing one independently like this. But nevertheless is the correct, that as you move parameters toward Earth-like values, or away from Earth-like values, very often things like the magnetic Prandtl number, the results get better, more Earth-like, right? So reversals are very interesting. So we get reversals in these fields, but I don't think there's been a single model that has gotten a reversing field that is also dipole dominant. These are mutually exclusive ideas. So we can get fields that have dipole by definition, because when you do a spherical harmonic decomposition, there will be an L equals 1 term. So there will be a dipole term. But in the ones that reverse, they're very weak. And, we've been hunting to get a model, by finely tuning the parameters to get one that's both dipolar dominant and also reversals. And it's a sweet spot that's hard to find, basically. So it's not something that is emergent from these results that is expected. And so it's another indication that maybe we haven't quite got things right. Yeah.
Might be pointless to run a simulation without an inner core for the early Earth if you're not really matching Earth-like.
People have started. Yeah, people have started to do that actually, and there's a current effort to do some model simulations without an inner core. So what you lose is that tangent cylinder structure, right? Some of the structures of the flows. So it would be definitely, people are interested in it. People are going to do it actually, I think. Dave, do you want to make a comment?
Well, I had a comment. It's interesting to contrast this difficulty with what happens
in the atmospheric science community
Yeah.
and in oceanography.
Yeah.
And maybe it's different. What I'm getting at is this, that when people do atmospheric circulation calculations, they confront some of the same difficulties. That is
Yeah.
to say, the viscous term is very small.
Yeah.
Now, with atmospheric circulation, it's not thermal convection in the way we think about the core. Nonetheless, some of the same issues arise when they worry about how to truncate their calculations. They don't put viscosity in, but a lot of what they want to understand turns out not to depend on that. Things like thermal winds, Hadley circulation and so forth can be done without the agony that Bruce has taken us through. And okay, so there are motions in the Earth's atmosphere like tubular convection and cloud formation and so forth, where these issues of truncation come in. That is, how do you handle scales that are smaller than the ones you can put into your calculation? And they seem to have gotten their way through that difficulty.
Yeah.
That is to say, they seem to come up with models that describe reality, and yet they don't depend on the actual value of the viscosity. And so the question is, why is the dynamo problem different?
Harder.
Now, it's interesting that in the oceanography case, one even has very distinguished people like Carl Wunsch who say that we don't actually understand ocean circulation, that these things you see in textbooks of nice, simple, large-scale motions are actually not right. And that is a small-scale problem. So oceanography seems like an intermediate case. But I guess in this rambling comment I'm making, what I'm trying to get across is the possibility that Uli Christensen could be right.
He might, no, absolutely right. Absolutely right.
Because some of the things that we want to understand might depend on large-scale circulation, and you can use large-scale circulation to drive the dynamo.
Yes.
So I could imagine a scenario where the small-scale motions that you're worried about actually don't matter.
Yeah, that's.
I don't know whether that's true.
That is absolutely possible.
And Uli, of course, has made the startling statement that none of the dissipative processes matter for the magnitude of the field.
But the thing is that these were the scalings. His were the scalings that I was showing you, right? These were the, and the problem is, of course, that the underlying assumptions that go into the model are not compatible with the results. So you have this is basically his scaling. So this, if you were thinking.
Yeah, I'm not disputing that the numerical simulations have a problem.
Right.
I'm just saying that maybe the answer.
Well, I think this is probably true. I suspect that is absolutely a true statement. And so I think the issue really boils down to the following, actually, and that is this issue of scales. And so my guess is that what's going to happen is as this number gets smaller, as this structure of flow gets smaller and smaller, my concern, I suppose, is that the small-scale flow is where most of the power is, and that there's relatively much less power in the large-scale flows, and that these might be the dominant engine of generating the magnetic field. Uli's point of view would be saying, don't worry about this stuff. It just will keep you up at nights, and it's for no reason. And it's really the large-scale flows that are ultimately responsible for producing the magnetic field. And that's absolutely possible. If that were true, then it means that we're probably within the realm of actually being successful at producing reliable models. If it turns out, though, as we make these numbers smaller, and as if most of the power, kinetic energy, ended up being dumped into these small scales, then I think we have to confront the fact that these small scales may actually be important. And the point is, and as Dave's absolutely right, we just don't know. And so, as you say, if you never hear about this work again, you'll know that Uli was probably right and I was probably wrong, actually. Okay, great, thanks.